So a lot of the reactions are going to come in pairs, and the first two are pairs. And when I say pairs, one reaction goes in one direction, the other is just the opposite. You flip the reactants and products around, and it's a different type of reaction that has a different name. So our first pair, formation is the first of the two. This is where elements combine to form one compound. Okay? So when I say elements, I'm referring to just one element in whatever its elemental form is combining with another element. Okay? My first example, I'll start with nitrogen as my first element. Okay? Now how nitrogen exists is as a pair, okay? As N2, and you've got that on the very front of your formula sheet, all those diatomics. Now nitrogen is a gas. It can react with oxygen, and it's another one of those diatomics in its elemental form. And now those elements are going to combine, and we're going to make one compound. Okay? Sometimes we'll make ionic compounds, sometimes we'll make molecular compounds. When you make molecules, in Science 10, you're not sure why it's one N and two O's. I need to give you the formula of the molecule that's being made. You would know it's a molecule because we've got two nonmetals here. Okay? Both of those are nonmetals, so this is going to make a molecule. Okay? This is a formation reaction, and last I will just balance it as a recap of balancing. And a lot of the skills this week are going to fit together. We're taking the naming that you learned, how to write equations, figure out the type, and balance. Okay? And those skills are all intermixed. Okay. To balance this, I've got two atoms to consider, nitrogen and oxygen. Nitrogen, they're coming in one pair at the beginning. So there's two of them in total. Here, there's just one nitrogen. Oxygen, there's one pair here and one pair there. So a pair being two. So my nitrogen isn't balanced at the beginning. I need to bring the one up to a two. So I need to double it. I can't just put a two here because now I'm changing that N to O ratio. I've got to double the whole thing. That fixes my nitrogen. It messed up my oxygen. Okay. I now have two NO2s. Okay. If you're not sure of the count, you could draw it out twice to get a bit of a visual. Okay. The shortcut is you're always multiplying subscripts by the number in front. So 2 times 2 is 4. There's the visual of the 4. I need to get the reactant side, that is 2, up to 4. So I have to double it. So I put a 2 there. So now I've done the formation reaction and I have balanced it. I'll do a second example and then we'll move on to decomposition. This one's going to be ionic. I'm going to start with calcium in its elemental form. Now all the metals come in ones. I'm going to react that with oxygen. And oxygen, as we just saw above, comes in pairs, and it's oxygen gas. A couple states you should be really comfortable with writing in or learning to put in consistently. Anything ionic by itself is going to be a solid, and that helps reinforce that super high melting point. Okay? All the ionic compounds melt at like 800, 900, 1,000, 2,000. So they're all solids, and all our metals by themselves are solids. Okay. So I react elemental calcium with elemental oxygen. I get an ionic compound, and you should be able to predict this. We're going to get calcium, we're going to get oxygen, and because it's ionic, a metal and a non-metal in the compound, you're going to use the charges to figure out what that formula unit should be. So either you've got that table up there, maybe you have your table close to you. What would the charge of calcium be? Pardon? +2. Okay, it's in group 2, So it's +2. Oxygen is in group 6. We've done this one a lot, so I'm not going to ask it. Group 6 is all -2 when it's paired with something. Okay. +2, -2, that's balanced. That's an ionic compound, so I know it's going to be a solid. I don't know its melting point off the top of my head, but it's, 1,000, 1,200, way above our room temperatures. Okay. Now I need to balance that. Okay. Now, one thing I just want to address quickly, sometimes students get confused. Why did he put in -2 there, but he didn't put in -2 here? Okay. I'm just using the charge in oxygen when it's ionic. So it's got to be paired with a metal. If you don't see oxygen paired with a metal or another positive ion, it doesn't have the charge. So up here, this oxygen is not paired with a metal. This is not ionic, so there's no charge here. Okay? Same, this is oxygen paired with itself. It's not ionic, there's no charge. Okay? There it is paired with a metal. Last, balance this. This one I'm just going to do orally, and then I'll move on to decomposition. 2 O's, one pair, just 1 O here. So I've got to double this side. Okay, I can't put a 2 here because I mess up my charges I just fixed. I've got to put a 2 in front. 2 O's in each side. I just doubled my calcium 2 times an invisible 1. 2 calcium. So I need 2 calcium to do that reaction. And then I'm encouraging you to put in that 1. Okay. So that's formation. Now we're going to go the opposite. We're going to start with a compound and go back to its elements. One compound breaks into its pieces, its elements. If you had 3 different types of elements in the compound, you'd have to break it into 3 pieces. Okay? Most of the time, you're going to have 2 elements in the compound, so you'll break it up into 2 elements. Okay? You could have 4 different elements. So I'm going to start with water as an example. Now this reaction isn't spontaneous, but you can get this to happen if you run some electricity through water. You can get it to break into its two elements. Okay. Those elements, we've got hydrogen. I'm going to have to come back and think of what is hydrogen's elemental form all by itself. And we've got oxygen, so I have to put that on my list. I've got 2 pieces. Now, how does oxygen come in its elemental form when it's all by itself? It comes in a pair. And again, so when you're writing the elemental forms, you're maybe flipping to this table to help you. It's got sulfur, phosphorus, and then all the diatomics. Metals, you have to remember, are 1s. Okay. Oxygen, we've done a lot. That's diatomic. And oxygen is a gas. Hydrogen is also a gas. We've got a pair of hydrogen in water, and we've got a pair of hydrogen here. We've got a single O in water, and we've got a pair of oxygen here. So the beginning, the reactance has half as much. We got to double this. Okay, I can't change water. I have to have 2 waters to get the 2 hydrogen. Now I've got 2 waters, 2 times 2 H's. There, I've got 2 times 2 H's. Now I got 4 H's on both sides. Okay. So we only make 1 unit of oxygen gas. I'll do an example of an ionic compound, sodium oxide. Okay. Metal and a non-metal, so I know it would be a solid all by itself. If I drop that in water, then I've got to use a solubility table like you have to predict its state. But this is all by itself, not in water. Going to do the decomposition. I got to break it into its 2 elements. One of them is sodium. The other one is oxygen. This is a metal. Metals elementally by themselves are come in 1s. Oxygen. pair again. Okay, we got a pair of O's, just a single O. So I've got to double my oxygen. Oh, I'm going too fast. I'm racing and I've made an error. This side is okay, but I've made an error at the very beginning by going really fast. Does anybody see what I've done wrong? Sodium oxide isn't the right formula unit. Yeah, I need 2 sodiums. I never balanced my sodium and my oxide. I didn't look at the charges. Sodium is 1 plus because it's in group 1, and oxygen in group 6 is 2 minus. And that charge is written right in. So I didn't balance those charges. So as was stated, you need 2 sodiums to go with the 1 oxygen. And if I'd kept going, the whole thing would have been balanced wrong because I didn't have that formula unit correct. Okay. Now, I'm good. I've got 2 O's here. I still just have the 1 O. I'm going to double my sodium oxide. I now have 2 times 2 sodium, 4. So I need 4 to get 4 sodiums. And we have 1 O. Okay. So that's our second type. Okay. Okay. Formation, decomposition. We're going to run into the next 2, which are often taught in pairs. They have some, they're not opposites, but they have some similarities. Single and double replacement reactions. We're going to start with single replacement, 1 switch, and then we'll move into double replacement where there's 2 swapping or switching of ions. Okay. One element replaces another atom in a compound. So we have an element and we have a compound. And in this compound, we're going to switch or replace something. Ag solid, silver solid. Okay. So what's the pattern? Because you need to be able to pick up these patterns and do the right switch. We've got elemental copper by itself. There's no charge here. Okay, it only has a charge when it's paired up with something. Okay? And the other chemical is our compound. Okay? We've got silver plus and a polyatomic nitrate negative. So +1, -1, so no subscripts needed. So there's our element and compound. Okay? And what we see is the copper take the place of the silver. There's our nitrate compound, and we replaced. We did 1 replacement and spit the silver out. Now, one decision you're going to have to make is which of these 2 should you pop out? And you have to sort of match charges. Okay? This is silver plus. That's nitrate minus. Okay? This is copper neutral at the beginning. So which one is it going to pop out? When copper becomes an ion, you have to think of, well, what type of ion is it going to become? A positive one or a negative one? And it's going to be positive. You don't have to memorize that. You go to your table and look at your copper and see what the most likely charge is. And it's positive. Okay. So this is going to pop out the positive ion. Okay, so because copper can become positive, it's going to pop out the positive one. If the element would become negative when it becomes an ion, then it would pop out the negative one. Okay. You're not going to get positive copper pair up with positive silver. Two positives would repel each other. That wouldn't make a compound. Okay. So copper is going to replace the silver. And you see charges swapping, and you'll always see this with the metal. The copper starts neutral, and it becomes copper 2+. The silver in the compound has a charge, and when it pops out all by itself, and it becomes neutral. And you'll always see this with the metals. The metal that starts by itself gets a charge. The one that starts in the compound loses it and becomes neutral. In 2 years from now, in Chemistry 30, we study these reactions in our redox or our battery unit. Okay? I want to mention it now, but we're not going to dive into the electron change. But this copper started with 0, started neutral, and ends up +2. The copper lost 2 electrons. 0 becoming +2. So if you can get this compound away from this one and connect them with a wire, you can get those 2 electrons to go through a wire and through your cell phone or through something that you want to use that electrical energy and make a battery. Okay? So these are going to really come up in our battery unit or our redox unit in a couple of years. Okay? Right now, you're not asked about electron exchange, but I want you to be aware of it. Okay? So single replacement, the element has to replace one of the other elements in the compound. I need to balance this. Okay? You can balance the N and the O separate, but when you see the nitrate stays as an ion, an O3, and then we got 2 of them here, you can count those ions as a group, and it just helps you to balance it faster. Here we have 2 nitrates. Over here we have just 1. So I can balance the N and the O fairly quickly by putting a 2 there. Okay? It now means we have 2 nitrates on each side. 2 N's and 6 O's on both sides. If we look at copper, there's 1 copper and 1 copper. It lost some electrons, but we're just counting the atoms. You know, there's 1 copper form to 1 copper form. If we double the silver here, we only have 1 here, so I have to double the silver. And now our single replacement is balanced. Our 4th reaction type, double replacement, we're going to do 2 switches. Okay. Cations in 2 compounds switch places, and we get 2 new compounds. So we had 1 compound up above, we're going to have 2 compounds now. So I have a lot of compounds to write, so I need every inch of my board. I'm going to try to be very neat. So PB, lead 2 nitrate is my first compound. Sodium sulfate is my second. So there's my compound and my compound. We're going to switch those 2 positive ions. I'm going to have to rebalance everything. So I'm going to go and take the sodium and stick it with the nitrate. I'm leaving a blank in here. We'll come back and talk about that state in a second. Now, sodium is a +1 ion. Nitrate is a -1. So they're balanced. I can't use the subscripts over here to help me. I have to re-look at the charges. Plus, minus. So that's in balance. Now I've got to re-look at the charges again. My lead is going to pop in where the sodium was. So we're going to have lead sulfate. Pb. Okay. This was lead 2 plus, nitrate plus 2 minus. Okay. It's helpful. You need to be aware of those charges at the beginning because they carry forward. Okay. There's no changes in charge here. Everything stays the same. Okay. So in the single replacement, you've got something by itself switching its charge. You don't here. So that was lead 2 plus. We still have lead 2 plus, and now that's going to pair up with sulfate, SO4. It's 2 minus there. It's 2 minus here. Okay. So you're not memorizing sulfate's 2 minus. It's on your polyatomic ion sheet. Very top is the ions, the middle is the elements, and the bottom is your periodic table. Okay. Okay. I'm going to balance this in a second, but I left these states blank. Okay. The original chemicals came in water. That's what the aqueous means. Okay. And we know they dissolved, so the ions all came apart. Over here, once you do the double replacement, you need to predict what the states will be in water, since it's still in water. So I'm going to, hopefully somebody can help me. If you have your periodic table, flip it to the back. You've got this big solubility table, and find nitrate. So you're finding it up above. So you looked at the solubility of selected ionic compounds in aqueous solutions at 25 degrees Celsius. And you see nitrate in that very first column. Okay? And then you go down. With most, it's aqueous, except there's a few options on the bottom. Okay? Do you see any nitrates at all in the bottom column, the solid row? No, there's no nitrates at all. Okay? I really try to, particularly my Chem 20s and 30s, but even Science 10, every nitrate is aqueous. If you remember, you don't have to look them up. If you can remember that, you know, there's no solid nitrates. You see a nitrate, you know it's aqueous. And that can save you some time. We've got to do the same thing to get our state of our lead sulfate. Our +2, -2, no subscripts. We got to start with the sulfate. Find that. It's in a column by itself, kind of in the middle. Then you go down. Sulfate with most things are aqueous. If we go to the bottom, sulfate will be a solid with calcium 2+, strontium 2+, barium 2+, lead 2+. That's what we have. So sulfate with lead 2+ will be a solid. You'll see flakes form. It's not going to make like a chunk, like a penny. It's going to look like, this would look like a snow globe. You get all these little chunks of solid lead sulfate, and if you left them, they would fall to the bottom like a snow globe would look if you left it. Okay? But don't think of a solid piece of metal. Think of like a whole bunch of sand or a powder is a better illustration. Okay. Balance this before I move on. Okay. Again, with these ion switching, we can count things in groups. We've got a sulfate and sulfate. We've got nitrate and nitrate. Okay. And we can count those in groups. It saves us time, particularly where we've got O's all over the place. Okay. This is really going to save you time. If you have the same count of nitrates on both sides and the same count of sulfate on both sides, it'll take care of your O's. So how many nitrates are over here? 2. Okay, we've got this subscript. Okay, so right now we treat this as a 1. Okay, we've got 1 lead nitrate and there's 2 nitrates in each. Over here we have just the 1 nitrate. There's no brackets or subscript. This 3 is part of the NO3 ion. Here we've got this 2 outside of the NO3. So we only have one nitrate here. We have to double it, and we have to do it by putting a number in front. Our sulfate, we've got SO4. There's no brackets or anything after the SO4, so it's one of them. Over here, there's no brackets or anything after it, so there's just one of them, so our sulfate is okay. We balanced our nitrate, we balanced our sulfate. If you counted all the O's, you'll find they're balanced. They just get balanced automatically. If the O's in both of the pieces are balanced, the O's will be balanced. What's left to check? Lead, 1 PB. There's no number there, a 1, and 1 PB. After this B is nothing, so we treat it as a 1. 2 sodiums, 2 sodiums. Okay? Every one of these units has 2 sodiums in it. Okay? So everything looks to be balanced now. So I'll just throw in some 1s, one of those, and one of those will make 2 sodium nitrates and 1 lead sulfate. Lead. Okay? I have to throw in the Roman numeral here. Because there's 2 types of lead, this is lead 2 sulfate, and that is lead 2 nitrate. Okay? I don't need the Roman numeral with the, to say the number of the Roman numeral there. Okay? So that's double replacement. We've done most of the reaction types. Now, some of the Science 10 teachers will do neutralization separate, okay? An acid plus a base. I like to combine it right in with double replacement, okay? Neutralization, acid plus base, okay? Because all students shouldn't think of an acid and a base as a different reaction type, okay? It's called neutralization, but it's just a double replacement. Okay? So an acid example might be HCl, aqueous. Hydrogen chloride by itself, but hydrochloric acid in water. Okay? It's a binary acid, 2 elements, so you use the word hydro. Okay? Chloric acid would have more than 2 elements. Okay? So there's our acid. Our base, I'll use sodium hydroxide in water. Okay? And they're going to neutralize each other. The acid and the base will neutralize. Acids have H plus in solution, which is going to be this H, and bases have hydroxide, okay? And that's the hydroxide. They're aqueous, which is telling us, you know, they're coming apart. Okay? And all you do is take this H plus, the positive is going to go with the hydroxide, okay? And the sodium is going to go and take the place of the H. So you have that first positive species just switches places, just like in a double replacement. So the H plus is going to go with the OH. Don't write what I'm about to write. So if you take the H from here and you pair it with the OH from there, you get that. Well, we typically don't, I wouldn't mark that wrong, but that's water. That's H2O. Okay? 2 H's and an O. But it's coming from the H from the acid, the OH from the base. So, you know, convention is, that's just liquid water. Okay. Then we've got the other switch. Sodium is going to go and now pair up with the Cl. Okay. That's sodium plus, that's Cl minus. +1, -1, so they're balanced. Okay? Now I'm not even going to check the solubility. How many have been in the Atlantic or Pacific Oceans? You know the salt's dissolved. It's not a solid precipitate. Salt dissolves in the ocean. So we know sodium chloride is aqueous. Our oceans are ample evidence of that. You could check your table and it would reinforce it is aqueous. Okay. I didn't end up using this was plus H and minus OH. This is, it's all 1 coefficient. It's balanced, okay? It doesn't always come out balanced. You still need to check your charges when you do a neutralization reaction from an acid and a base. So we've done formation, we've done decomposition. We did single replacement, we did double replacement, and then I tuck neutralization in with double replacement when an acid reacts with a base. One left, and then you'll have a bit of practice time, and at the end I've got some, I'm going to carry out the lab, but you're still going to do a purpose hypothesis observations. We're just not doing this in normal groups. Complete combustion, hydrocarbon combustion. So what are hydrocarbons? We'll spend a whole unit in grade 12 just on hydrocarbons. They are compounds of C and H. They're your fuels. You go to the gas station, you buy fuel. You want to go camping, you buy camping fuel. You fill up your barbecue tank. All of those are hydrocarbons. And I'll do an example of the two most common hydrocarbons you might have at your house. The first one is methane. If NMAX or ATCO gas has gas coming into your home, it's methane. Your stove or your furnace is probably burning methane. That's our hydrocarbon. The rest of the pieces, when you see the word combustion, which I'm underlining in red, all of these pieces you have to realize. When you burn something, you are burning it with oxygen. That's the other reactant. I don't have to say it. I just have to tell you the blue fuel. The products of hydrocarbon combustion are always these two products. One of them is carbon dioxide. You take the carbon and you saturate it with as much O as you can, and you get CO2. Then you take the hydrogen and you saturate it with as much oxygen as you can. And what would you get when you fill hydrogen up with oxygen? You get water. Now, we don't see it. We don't see the liquid pouring out of our barbecue because it's water vapor. But in winter, you see it sometimes. It's really cold out and there's a car driving in front of you and you see that like frost coming out of the tailpipe. That's water. It's the water vapor coming out of an automobile and freezing because it's so cold. And then you can see it. So the red is something you need to memorize and realize. The blue fuel I need to give you. So we'll balance this. Okay, we've got C's and H's and O's. Okay. So if you want a systematic approach, you would make a list for each of these. I've been doing them orally a bit. I'll write them out quickly for this. Carbon on the reactant side. There's 1 in our methane. There's 1 in our CO2. Hydrogen. 4 of them in our 1 methane molecule. In our water, they come in pairs, and we've got 1 pair. Oxygen. 2 of them there. On the product side, they're everywhere. We've got 2 of them there, and we've got 1 of them there. We've got 3 in total. So don't start with your O right away. You kind of want to end with your oxygen when you balance combustion. Okay. So our carbon started off okay. Hydrogen isn't balanced. We've got to double this 2. We have 4 H's. We have just 2 of them here. So I'm going to have 2 waters and double our H. That also doubles our oxygen. Or sorry, not doubles, it doubles it here. We still have 2 there, and now we've got 2 here. So the 3 goes up to a 4. Now our oxygen is low on this side, the reactant side. We need to turn the 2 into a 4. So we need to double our oxygen. Instead of 1 pair, we need 2 pairs. And now our combustion reaction is balanced. If you started with the O's, you'd probably not solve it. You kind of get in a bad loop. Second example, this one's going to be much harder. This example is going to stump a lot of Science 10s, and unfortunately some Chem 20s are going to struggle with this, but I'm going to show you a shortcut. This is propane. So if you have a barbecue, if you have a barbecue at home and you've got a tank sitting underneath it, it's probably propane. I'm going to do the combustion of propane. That's all you might see on a test. What is the combustion of propane? It's C3H8. You would go, okay, that's combustion, hydrocarbon combustion. Oxygen makes CO2 and water vapor. The red I expect you to realize. Okay. Now for the shortcut or the help. Okay. If you start to balance this, you're going to end up with an odd number of O's here that you can't fix. After you C and H, you'll be most of the way through the question, and you're going to have an odd number of O's, and they're going to come in pairs, and you're going to be in trouble. Because you can't, this side has to be even. Okay. Now, I know that, did I do that right? Oh. So fix a typo and then this. There, now, so I had a 4 there originally, it's 6, in which will follow what I want to do. Okay. So all of the hydrogen has to go into the water. There's nowhere else for it to go. And right now, if you think of how many pairs you're going to need 3 pairs. We start with 6. You're going to end up with needing 3 pair to get to balance. And that's an odd number of O's. Okay. Anytime when you take your hydrogen and you go to balance it and you get an odd number here, you're going to run into trouble. And to fix it really easily, double that fuel and it's going to solve that odd number problem. And then everything is going to balance nicely for you. Okay. So what I did, when you take the H count and you divide it by 2, okay, and what happened was I got an odd number. Okay. Up here, I took the H count, when it got divided by 2, it was a 2, and that's even, and everything worked out nice. Okay. Here, this 6, when I divided by 2, I got an odd number. That was going to cause, I didn't get to that problem, but I would have had an impossible solution. Okay. By doubling it, now we're going to have an even number and everything's going to work out. I now have 2 times 6, 12 H's. Okay. Well, how do I get to 12 in pairs? I need 6 pairs. Aha, I've got an even number again, and that's what I wanted. So 6 times 2 hydrogen, 12. 6 times 2, 12. I want to do my O's last. My carbon I can fix 2 times 3. There's 3 in each molecule. There's 2 of them. There's 6. I want to need 6 CO2s. Last, I'm down to oxygen. Okay. Even I find these hard to do in my head. You end up getting a bunch of oxygen. Please write it down. I'm going to do this side where there's O's in 2 places. 6 pairs, 12. but we're not done. 12 plus the water. There's 1 O each, and there's 6 waters. 6 times 1, 6. So there's a total of 18 when I put the CO2 and the water together. Okay. If I didn't do what I did before, I'd end up with an odd number here, and I wouldn't be able to say how many pairs make 7. Well, there's no answer to that. It's not a whole number. Okay. How many pairs of oxygen do I need to get 18? 9. And it balanced. Okay. And these can be pretty quick if you realize this at the beginning. Okay. The hydrogen divided by 2 was odd. Okay. And the combustions kind of always fit into one of these two types. Okay. I just had an error at the first. I put in 8, which wouldn't have, 8 would have worked out nice and quick, and I wouldn't have needed to do that doubling. Okay. So those are your reaction types. The first thing I'd like you to do is go back to your workbook, and you could finish that page 16, I believe it is, that has the balancing and the reactions on the side. If you're not done that balancing, you could finish the balancing, and now you can look for these reaction types and write in which type of reaction is it in the blanks. If you finish that quite quickly, you can move on and start working through those word problems. Okay? That are very slow. They take a lot of time. You might spend 5 or 10 minutes on every one of those lines on page 17 in your workbook. Words to formulas, to equations, and balancing it.